So looking at number 6, is let's find the angle of intersection of the planes given by x equals this. X plus 9y plus 7z minus 22 equals 0, and y equals 3. So, and then round your answer to the nearest degree. So if we want to find the angle of intersection, it's not simply a matter of just finding the intersection. What we would want to do is find the angle of intersection between the normal vectors that guide these planes. All right, so this one has a normal vector, so I'll call it, it's a little thick now. I'll call it N1, it's still thick. 197, and N2, 0, 1, 0. All right, because there's no x term, there's no y term, which means their coefficients must be 0. No x term, no z term, so their coefficients must be 0. The y term has a coefficient of 1. All right. So what we would want to do is use our cosine rule, which is cosine of theta is equal to n1 dot n2 over the magnitude of n1 times the magnitude of n2. All right, so n1 dotted against n2, that part's easy. Super easy, barely an inconvenience. Because you're multiplying the corresponding parts and then adding the results. So the only thing that doesn't zero out is the 9 times 1, which is 9. So that's done. The magnitude of n1 is really the only thing that's going to require even the slightest of effort, because the magnitude of n2, it's one of those unit vectors, which is just going to be a 1. So we're looking at 1 squared plus 9 squared plus 7 squared. So 81, 82 plus 49, so 130, is that 131? Yeah. I'll double check. It sure is. All right, so 9 over, really, that's the product of these two things. So 9 over the square root of 131. And now I see that my fraction bar is just way too big. So if I want to find the angle, I would say the cosine is an inverse of 9 over the square root. And that took off on me. I can live with that one. Square root of 131, that's going to be my theta. So inverse cosine 9 divided by the root 131, and the angle would be about 0.66, well, 666 radians. If you're interested in what that looks like in degree form, just kick it over into degree mode. You see it's about 38 degrees-ish. And so radian mode is, oh, it did say nearest degree, huh? So we're more than interested. It's a requirement of the problem. So approximately nearest degree, so 38 degrees. And so to address the question that wasn't asked, what if they said to find the equation of the intersection? All right, so we would go back to our original, which is x plus 9y plus 7z minus 22, but I'll write plus 7z equals 22, and y equals 3. So we can make a substitution, and that would be that y is getting replaced with a 3, a known value. So that gives us x plus 9 times 3 plus 7z is equal to 22. So x plus 7z, I'd be subtracting 27 from both sides, would be negative 5. I could solve for x, really, z, if I want. X equals, it's easier to solve for x, so negative 5 minus 7z. And so I have y, which is defined as a constant, x, which is defined in terms of z, and there's no way to solve for z in terms of y or x in such a way that I'd come up with a unique equation. So what I would say is that z is the free variable. And so we would get our set of equations. X is equal to, well, even before that, I would let z equal t. And so I would say that my x equation, so intersection, I'll put it as a vector valued function, would be negative 5 minus 7t. The y component is just a 3, that's constant, and the z is what we defined as t, so our vector value function would be negative 5 minus 7t, 3, and t. For number 7, we have to write the equation of the line passing through those 2 points. So what I would want to find is the parallel vector, so I'd focus on line L. So the parallel vector (5 minus 6, 1 minus 5, 2 minus negative 2). Poor quality close bracket there. So negative 1, negative 4, positive 4. All right, so my line equation, I'll call it L equals, would be the vector valued function. I choose to start it off or pin it at the initial value 6, 5, negative 2. So 6 minus 1t, 5 minus 4t, and then negative 2 plus 4t. Now for line M, much easier. Lime? Okay. We're given the parallel vector, so we're good there. We could just go right to it. M would be equal to, because they gave us the fixed point, negative 7 plus 1t, 10 plus 1t. I'll just write the t. I'm doing that all along anyway. Negative 7 minus 1t. And again, I can't stop myself from making those terrible closed brackets. All right. So we're looking for an intersection here, if it exists, really. But we do that by finding a system of equations based off of the equality of corresponding parts. All right, so I'd set this equal to this equal to this, and this equal to this. The thing is, as we talked about throughout the unit, not all of these t values are living in the same universe. So a subscript, this is t1, t2, t1, t2, t1, t2. So 6 minus t1 would be equal to negative 7 plus t2. That means there's some t value in the first line that could equate the x component to the x component in the second line with its corresponding t2 or t value. So 5 minus 4t1 equals negative, oh, sorry, we're reading the wrong thing, even though it's color-coded. 10 plus t2, negative 2 plus 4t1 equals negative 7 minus t2. Get your t's on the same side, get your constants the other way. So I'm going to, in the first one, add t1 to both sides. So t1 plus t2 equals 13. I'm going to add 4t1 to both sides. So 4t1 plus t2 is equal to negative 5. And then here, in the last one, I'm going to add t2 to both sides. So 4t1 plus t2 is equal to, and then I'll add 2 to both sides, so negative 5. All right. So it looks like my second and third components are identical, which should make things interesting. All right. So just double checking, because you never know. Sometimes I've been known to make a mistake or two. I'm not seeing one, but that doesn't mean it's not there, so we'll just be on the lookout for it. So anyway, the coefficient matrix, 1, 4, 4, 1, 1, 1, 13, and then augmenting with the solution values, 13, negative 5, negative 5, which I'm going to RF to get the simplified form. So let me get a, oh, I don't have a matrix calculator up. Desmos.quam/matrix. Oh, start typing. And you get there eventually. New matrix, 3 by 3, 1, 1, 13, 4, 1, negative 5. It's not a 1. Look at that. 4, also 1, also negative 5. All right, so reduced row echelon, matrix A. Lock it in. So we're looking at 1, 0, negative 6, 0, 1, 19, 0, 0, 0. So as it turns out, regardless of the look of the equations, if they simplify to give the same form, they're actually the same linear equation, right? So it actually means that this one was irrelevant, all right? It wasn't necessary. So we could have actually dismissed it and came up with a 2 by 3 matrix, which would have gotten the job done, all right? Which is really, I think, evidence based off of what you see in the solution matrix, because that 0, 0, 0 indicates that, yeah, you'd have a free variable if it was a third variable, but there is no third variable, so everything that we needed was taken care of in the first 2 rows. All right, so it's kind of consistent. So that's what I meant by an interesting situation. It also tends to indicate that you're going to be looking at a solution, right? Because there's no way to get a contradiction in the third row if the third row is just going to zero out anyway. All right. So, but regardless, so T1 is going to be equal to negative 6. T2 is going to be equal to 19. The fact that we got unique solutions tells us that we have an intersection. They are asking for the coordinates of the intersection, though. So what I'll do is I'll just grab my L's and M's, my L and M equations. And, since this is a test, I would certainly want to make sure that I'm double checking my work. So I would not get lazy here. So I would be looking at L of -6 and M of 19 to verify. I would do them both to verify that it's going to play out correctly. Plug in a -6 and you're going to get a 12. Plug in a 19, you'll also get a 12. -6, so 5 plus 24 is 29. 10 plus 19 is 29. All right. -2 minus 24 is -26. And then -7 minus 19 is also -26. All right. So they both point to the same vectors. Those vectors terminate at a point, the intersection would be at 12, 29, -26. So number 8, we're asked to do a variety of things. Derivative, limit derivative, antiderivative. The one thing we're not going to worry about for this test is the curvature, so I'm going to squeeze that one out of there. There you go. Goodbye. Goodbye, curvature. Get you in Unit 2. All right, so for Part A, the limit as t approaches 0 of r of t, very straightforward. We're replacing all of our t's with zeros, in this case zeros. So 3 sine of t, so 3 sine of 0, 3 cosine of t, so 3 cosine of 0. Alright, so we're talking 0, sine of 0 is equal to 0. Cosine of 0 is equal to 1, so 3 times 1, 3. Alright, so that's not bad at all. Now, for Part B, it's asking for continuity, so we would look at each component individually and just kind of conjure up our inner Calc 1 self and say, alright, well, what would be the continuity associated with a linear function? Linear functions are everywhere continuous. What about an ordinary trig function like a sine or a cosine? Everywhere continuous. So this is continuous on the interval of -infinity to infinity. All right, so there it is. That's pretty nice in terms of a continuity question. All right, so there's more challenging ones from the notes and from the other practice assessment. So definitely take a look at those if you want a more beefier version, but this one wasn't bad. All right, the derivative, d dt of r of t. Differentiate each component. So derivative of 4t, 4. Derivative of sine is cosine, so 3 cosine. Derivative of cosine is negative sine, so -3 sine t. So then D is asking for the antiderivative. So we anti-differentiate each part. 2t squared plus integration constant number 1, first dimension, comma, antiderivative of sine is negative cosine. So -3 cosine of t plus c2. And then antiderivative of cosine is sine. So 3 sine of t plus my third integration constant, or the integration constant associated with the third dimension. Either interpretation is correct. All right, so there you have it. Again, we're not bothering with the curvature question for this unit, so that's all she wrote for. So last but not least is the word problem. Boat sets sail in direction 45 degrees north of west with a speed of 32 knots in order to compensate for wind that's blowing in a direction of 30 degrees north of east at a rate of 12 knots. Find the component velocity of the wind acting with or against the direction of the boat. And then round that to the nearest 2 decimal places. All right, so let's get a set of coordinate axes here. Oh, okay, that was interesting. Okay, kind of looks cool. Not what I was going for, but I'll take it. So 45 degrees north of west, which I guess would be the same thing as, oh, look at that. This is all falling apart. It would be the same as 45 degrees west of north. 32 knots in order to compensate for a wind that's going 30 degrees at a rate of 12 knots. So this one would be much shorter, but also the angle would be 30 degrees. All right. So would it be that much shorter? I don't know. That's not the point. It's just the size relationship would be that there is one. How about that? All right. So we'll call this one, we're talking about a boat. We'll call this B, and we're talking about the wind. So we'll call this W. They're telling us the boat is moving at a magnitude of 32. And it's 45 degrees north of west. So that's telling us if we're going with the x-axis, that would be 135 degrees. That's a little blurry. That's good enough. All right. The other one is 30 degrees, so I could just kind of tuck that in there. All right. So we need the component velocity of the wind acting with or against the direction of the boat. So out of all the places I could have put that, number 30, I chose literally the worst place. So I'm just going to move that over a little bit and kind of do something like this. There we go. So I'm going to straighten that out. Not really, right? Want it to be something more like that because I want to be able to drop an altitude down to the extended vector B. All right. This little, that shouldn't have happened. This little guy here, that's the thing that we're looking for, which is the projection of W upon B. All right. So ultimately we want the magnitude of the projection of W upon B, which is going to be the dotting of B and W divided by the magnitude of B. And that'll tell us what amount of the wind is impacting the movement of the boat. All right, so we know that the magnitude of W is, they told us 12. We have some angles. So what we need are actually B and W. All right, so B would be 32 cosine 135, comma sine of 135. W would be 12 cosine 30 sine of 30. All right, so if we dot these two together, B dot W, 32 cosine 135 cosine 30 plus 12 sine of 135 sine, oops, apologies, I knew I missed something. 32 cosine 135 times 12 cosine 30, and then 32 sine of 135 times 12, little dot for the I, times 12 sine of 30. All right, so we can factor out a 32 and a 12, and that's going to give us cosine 135. So cosine 135 cosine 30 plus sine of 135 sine of 30. Just going to smidge some stuff around here. All right, so I'm still going to leave this as 32 times 12 cosine. It's this is the difference identity for cosine. So cosine 135 minus 30. So 32 times 12. I mean, we could actually figure out based off of what we have here. But since we got to go into decimal form anyway, we might as well come up with a simpler thing to type into Desmos. So cosine 105. All right, and so from there I can pop into my formula because now I know my B and W. (32 times 12 cosine 105) over the magnitude of B, which is 32, cancel, and we would be left with just a simple calculation. 12, I have it still from previous problems in degree form, so 12 cosine 105. So we're talking negative 3 point, they said nearest two decimal places, negative 3.11 knots. All right, so this is actually pulling a little more than 3 knots away from the potential speed of the boat. And that's just because of the wind, which is blowing at 12 knots, so it's not fully impacting in the negative direction the speed of the boat, but it is having some